This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hello, I'm Lee Bortons, and it's Wednesday, September 18th, 2024. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss lessons each week from our math curriculum for families with students enrolled in classical conversations communities. Our club is preparing to continue the first semester of the Math Map and our Challenge 8 program, as well as all the families that are using it with their children that are not inside our very first communities of Math Map students. And we just appreciate how many of you folks aren't waiting, but are jumping on board right away. So thanks for joining us as we work through a lesson a week and work on strategies and highlights for each lesson. Kirsty, what do you have for us today?
Well, we are wrapping up the first dimension today, looking at lesson 8, equations. And so always every week, we're going to take that opportunity to make sure we know where we are on our map. And so go ahead and look at the map in your booklet. And we are, once again, we are here on week 8. And then you want to go ahead and find the color and the name of your domain that is on your booklet cover. We are working through the complex, so we are working down this way, which puts us right there on the map. So go ahead and make a check mark so that you know where you are.
Kirsty, maybe next week we can revisit all the reasons that we do this. It's been a while since we talked about just the map itself.
Absolutely. So we're going to warm up our computation math brain. So I'm going to hit our timer here to start our countdown. And then let's go ahead and see how many board numbers we can knock off our board with 5, 5, and 3.
5 times 5 equals 25 plus 3 is 28.
And minus 3 is 22. And plus 3 to the 0 is 26, and minus 3 to the 0 is 24.
5 plus 5 plus 3 is 13.
5 plus 5 plus 3 to the 0 is 11.
5 plus 5 minus 3, 7.
5 times 5 plus 5 plus 3 times 3 to the 0. I'll get this. And then minus 3 to the 0 is 9.
5 times 5 plus 3 squared is 34.
5 minus 5 plus 3 is 3.
5 to the 0 times 5 to the 0 times 3 to the 0 is 1.
And plus 3 to the 0 is 2.
5 squared plus 5 plus 3 is 33. 5 squared plus 5 minus 3 is 27.
5 times
divided
plus
5
5
divided by 5 is 1 plus 3 is 4.
5 plus 3 is 8 times 5 to the 0 power is 8.
5 plus 5 is 10 times 3 to the 0 power is 10.
And 5 plus 5 times 3 is 30.
5 times 3 is 15 plus 5 is 20.
5 times 5 to the 0 times 3 to the 0 is 5.
5 squared is 25 times 5 to the 0 plus 3 to the 0 is 25.
I think that's the closest we've gotten to knocking off the entire board. Well done, everybody. All right, let's go ahead and take a look at our cover. I certainly encourage you, if you have this, to use the copy you have in front of you versus what's on our screen. But I wanted to challenge you to specifically think about the fact that today is our capstone lesson for 1D. And what I mean by that is that we're going to look at equations, and where in each of our operational lessons, we looked at comparisons, and then we looked at addition and subtraction, multiplication, division, and then exponentiation, roots, and logarithms. So we looked at each of those individually. We're going to look this week at putting all of those together into equations, and what does that look like. So it's really an opportunity to review what we've looked at, and as well as integrate what we've looked at. So I would like you to take a picture, look at this picture, this artwork here, and tell me, what do you see here that looks like math, arithmetic being done on a number line? So think back over our last few weeks and tell me what are some things here that you could pull out from this piece of art that help you to review our 1D lessons.
Well, the people on the bench are going across, which would be sort of like a number line, but then also thinking of equations, the back of the bench looks like an equal sign.
And the lamppost looks like it could be the 0 point on that number line.
I was right away thinking about how with that number line of people, we choose an origin, you know, maybe saying the little girl with the red hat, 3 people to the right is someone I'm trying to point out.
The horses can almost be like the hops or the vector arrows.
Good.
I was going to say, generally, it looks like there is order and arrangement, like there's direction as well.
Yeah, the hops or vectors are going in the negative direction, aren't they, with the horses?
I thought the little girl, there's a little girl in blue and that little girl in red. I thought they could be like the halfway marks, you know, like the grown-ups could be like the numbers, and the little people could be like the halfway people. The people on the benches make me think of inclusive groups.
The people in the carriages make me think of exponents.
I was thinking of the people in carriages in our community. We just finished addition and subtraction, and just thinking like, you know, people coming into a carriage and coming out of a carriage is addition and subtraction.
It also reminds me of the real number line, that there could be 2 people who are 5 years old or 25 years old, but if you narrow that down to what month were they born, what day were they born, what time were they born, there's always another increment in the middle.
It reminds me of if you were seeing it even as like a grid for like the number line, if that was the x-axis with the bench, that if you were walking toward the lamppost, I can't help but think of Narnia, like walking toward a lamppost, but you know, might be on that y-axis walking toward the lamppost, heading toward that x-axis.
Or Deborah, which axis have we been looking at in these 1D lessons? We haven't really looked at a y-axis, but which ones have we in the complex lessons?
The x-axis, just like that horizontal.
The x, and then which one have we been looking at that's been vertical on our page? Anybody?
I don't know.
For the imaginary number line?
Imaginary axis.
Oh, okay, yeah.
I like how there's that little bit of light sky, because it's like drawing me to the idea that, oh, there's even more dimensions possible.
So when we think of our operations, we've thought about the fact that we could count, right? And if we were counting, right, our people might be our best way to help us see how we count. We move, right? They're seated people, right? As we count, we're moving one unit in either direction. Then we have people that are walking, in either direction. And then we have the horses in either direction. Which are moving faster? Those that are walking or the horses?
Is there a way to tell this?
Well, what just thinking, what do you think? Would a horse drawn cabbage move? Cabbage would move. Would a horse drawn carriage move faster, or do you think people walking would move faster?
What, the carriage?
The carriage probably. So if we thought about our operations and we think about, say, addition and multiplication, does one of those sort of move faster up and down the number line than the other?
So you're getting at the people are kind of like addition, subtraction, but the horses are more like multiplication.
Yeah. So multiplication would move faster, exponentiation even faster.
Even faster, yeah. So there's a way we can kind of look at that comparatively in this picture.
We need a bird in the picture who's flying.
Well, I would say that the trees could be exponentiation.
Okay. Well, good job. So here's a great example of how our art really has been chosen specifically to help us each week, not just to look at the things that we're looking at in that particular week, right? But also to be a place to help us integrate our ideas together as we look at math, right? We don't want it to be little disconnected pieces, but we want to integrate it together. And so the art gives us an opportunity to do that. Great. Well, let's go ahead and look at our invention page. And as we look at this, I'm going to draw your attention to where it says one equation with one unknown. And that may be an unfamiliar way of saying something, or it may be familiar, but I wanted to ask you to tell us everything that you know about one equation with one unknown.
One equal sign.
One equal sign.
If there's an unknown, I'm looking for a variable. Like to me, I'd be looking for some sort of number or letter. Sorry.
Okay, good.
I feel like if
Any of
it's
those.
one variable, I could solve it.
Yeah.
Good.
That's good. So in contrast to what you just said, if it had been one equation with two variables, I'm not sure I could solve it.
What other things might one equation with one unknown have? So we said one equal sign, and we've said one variable. What else would it have, perhaps?
It's gonna have either like multiplication, subtraction, multiplication. Like it's gonna have a sign telling us what we need to do.
Okay, great. So we're
Maybe
gonna have
one
some kind of
answer?
operation. Yeah.
Just one answer?
Okay, so there may be one answer. Notice I said maybe, so we can talk about when maybe it would have more than one answer.
It does say solve, not just simplify, which that tells me that I'm probably going to come up with an answer.
Okay, so we think there's going to be a solution. We're using this word solve. So we've got one equal sign, one variable, operations. What else might you see in an equation with one unknown?
Possibly like terms that we can apply.
Okay, so some numbers, right? There's got to be something else there with our variable. If I just said x equals, you'd all be sitting there waiting for me to say x equals what, right? So we know that there's got to be something else there, whether it's a parameter like x equals a, or whether it's a number x equals 4, that we have a variable, we have an equal sign. Usually we're going to have some kind of operation, and then something else, some other kind of term or number that we're going to be working with. Okay, so we're kind of familiar with this idea of one equation and one unknown, whether or not you like solving equations with one unknowns, right? A lot of us are somewhat familiar with that. So now let's take a look at something maybe you're less familiar with. So I want you to look at the line that says simplify expressions, and then GIMA. So that's up here. And then this one here, solve one equation with one unknown, AMIG. And you don't necessarily have to know everything that this is about. We're going to talk about it again in a few minutes. But I just want you to use your skills of comparison and compare those two lines.
They almost look like they're opposites of each other, because in one, you're looking at groups, indices, multiplication, division, addition, subtraction, and then solving one equation with one unknown value. It's almost like you're reversing the process.
Excellent.
One says simplify and one says solve. So the one that says simplify looks like it's already been solved. We just need to simplify the things that are in that expression.
Okay. So there's another thing we can talk about, right? So you just said simplify, and then you said expression, and then what word goes with solve?
AMIG, you mean?
No.
Equation.
So it says simplify expressions, and then it says solve what?
Oh,
Equations.
Equations. So what's the difference between an expression and an equation?
An expression doesn't have a equal sign, right?
Correct. So if I'm looking up here, this part here, that's my expression, right? Just one side of my equal sign is my expression. So we're using an equal sign to show what the simplification is, but that expression is just that left-hand piece, or just the right-hand piece, right? But it's just one side of my equal sign. Whereas my equation, we all said, hey, that has an equal sign. So this whole thing is my equation.
So expressions are parts of an equation. Okay.
They are.
The fact that you have the answers to the simplified expressions confuses me just a little, because it makes it look like an equation that I'm looking at. But there's nothing to solve, so I guess that, but do you understand what I'm saying?
I do. It is, and it does feel like you're like, but there's an equal sign. So that's where we have to pull back and go, okay, well, which part of this is my expression? And so which part am I simplifying? I'm just simplifying on one or both sides, right? So if I wrote something that looked like this, right, I could simplify both sides, and I can replace this with 2x, and I can replace this with 10. So I have simplified each expression. I've simplified both sides of my equation. Now, if I wanted to solve, right, so this right here, what did I do? I simplified. Now, if I wanted to solve, right, this is my solving here, right? And so oftentimes solving may involve simplification first. Okay, and we'll talk, right, we can talk a little bit more about that. But I really want to point out that most of the work that we're doing from the digits domain through the complex domain, we're up here, and we're going to be simplifying expressions. So if I asked you to right, if I said, okay, look at that, even if I put the equal sign there, what we're doing is we're simplifying, because what we want to do is we want to replace this one expression with another expression that has all the operations have been performed, right? We've gotten rid of any, we've combined any like terms where we can, we've cleared any exponents or indices where we can. We've done all of the operations that we can in order to replace this with something that is simpler, hence it being called simplifying. And that's, so even though we wrote that equal sign there, what we're doing is simplifying. When we talk about solving, this is when we're going to start looking at algebra, because we're going to be using that unknown. So over here, what did I do? I found a value that made my equation true. Right. So I found the one value that made this equation true. And so that's when I'm solving, is I'm finding that value. And so usually when we're talking about solving, we're going to be talking about some kind of algebraic expression that has a variable in it. So this is going to start in monomials and on. This is going to be digits through complex.
So if I wrote a math problem, like a very simple math, like 5 + 2.
Yes.
And I was writing a random worksheet, would I say simplify 5 + 2, or would I say solve 5 + 2?
I would say simplify 5 + 2.
Okay, great. I've never seen that distinction before. Thank you.
But if you said 5x + 2, we would say, give us one more piece of information and solve it. Because you got that x is in the middle of things.
Gotcha. Okay.
And what if you said 5 + 2 = x?
You simplify the left side.
Okay.
And there is that little kind of nuance there, right? Like I'm kind of solving it, but I didn't really do anything to solve it. I just simplified. And so you may see that in the complex lessons. You may see that there are places where as the scaffolding, right? We're scaffolding the math map. We're working up towards students being able to handle all of these complex equations. So this year you might see something where they end up with this, right? Where Lee has broken down the steps and given them all of the steps that would have been the algebraic solving and left them with this because all they're really doing is simplifying.
Right.
So, so that is part of how the math map scaffolds this idea. All right, so we're going to talk specifically about the GIMA and the AMIG, GIMA and AMIG. We're going to talk about those again in a few minutes. But what I wanted you to see here is that GIMA that goes with simplifying expressions, and the AMIG, which I forget who it was. It said that's the reverse. It exactly is the reverse. That goes with solving equations. All right, so that's the big idea to hold in your head.
What I thought of, Kirsty, when you wrote that 4 × 3 - 1 squared, is simplifying is in essence showing our work.
Yeah. If you're a good student, it's showing your work.
Yeah, but that's, that's our big struggle with some of our kids, is that they just give us an answer and it's like, well, no, how did you get to that answer? Show me your work.
You're right.
So,
and that's,
but yeah.
We're going to talk when we get to lesson 22 and we look at, or back in lesson 1, we have it a little bit in our charts there, but we're going to also look at it in lesson 22, is taking these skills of learning and these canons of rhetoric that we apply to all these other things. And we think about, well, what can that teach us about math, right? And that idea of delivery and elocution, that to me is exactly what you're talking about, is teaching our students that if you're going to deliver your work well, if you're going to elocute, right? If I'm going to present my work in a way that is pleasing to others, then I'm going to show that work. And so part of that elocution and delivery is exactly what you were talking about, is showing our work and being thorough.
So one of the things that messes us up in math is because when we first start working with mathematics, the answers are simple, and we want that simple thing to continue. And a better use of a more mature mathematician's time is to not worry about what the answer is, but to try to figure out why the patterns and the steps and the processes are what they are. And so parents say all the time, I want my child to understand the concept, but as soon as you give them a math problem where there's not an answer key, they're upset. Right, so we have like emotional habits that we have to break. And so I'm really happy that Kirsty came up with this GEMA and AMIG, because simplifying and PEDMAS, which is what we all did, is pretty much what we think all of math should be. And it's just not true.
All right, so let's look at our I cubed page. We spent a little bit more time on our I squared page today, so we're not going to spend as much time here. But I did want to take a minute to point out to this. This looks like it's this really long list of operations. Have we talked about all of these operations already at this point in our year? Have we studied science?
No, we have not.
We have not. We have not, right? And so notice that this is a great example of where Lee has pulled together ideas that normally would be on their own charts, right? So we had our addition and subtraction charts, our multiplication charts, our roots, exponents, and logarithms charts. We're going to have a trig chart. But this chart helps to bring all of these together into one place as one sort of master reference. If I was a student in my first year, I would look at this and go, right? So our job as parents, as teachers, is to say, well, we're not trying to learn all of this yet, right? Maybe we can just read our operations. Those all look like English words that we can probably read. And then maybe we can look at the notation to the right of it so that when we see it again later in the year, we go, oh, wait, it's a little bit familiar to me now. The other thing is that I'd like to pull your attention to the very top of the page, right? That if there was one thing that I was going to encourage my students to memorize this week, it might be that information at the very top, that general math model, where we have input and then some kind of process, and then we have some kind of output, right? And we see that that's most of what we do in math is all covered by this general model of taking numbers, expressions, or functions and doing something to them and getting either numbers, expressions, or functions out. And so if there was one thing that I was going to really focus in on this week in terms of adding to my memoria, it would probably be that. And then understanding how what's underneath takes that middle box and tells me what are some of the things I can do in that middle box. And as I look at those things I can do in that middle box, what might that tell me about the kinds of numbers I can use? And that's what this is summarizing here. Right? So let's go ahead and take a look at our charts. And I'm going to give you just a minute or two to talk about things that are familiar and unfamiliar. And then we're going to dive a little bit deeper into why we use GIMA and AMIG. So everybody's looking for one thing that's familiar or one thing that's unfamiliar.
We just looked at all the operations that are on the bottom left on our frame.
Yes, and some of those are familiar, like we said, and then the ones toward the bottom, derivatives and integrals, I've heard those words, but I still have no understanding of them.
Good.
Where it says domain, and then I see all the notations of the domains that are becoming more and more familiar now.
Mm-hmm. I see the quadratic formula.
I see the word secant, and I have no idea what that is. That does not ring a bell at all.
And that's okay, right? So I just want to encourage all of us that it's okay if you don't understand everything that's on these charts, because our kids need to hear that it's okay that we don't know everything, right? That our kids like to think that we know everything, just like, I don't know if we have any men on here, but women, You know what I mean. What do your husbands do when they want something? Do they look for it or do they just ask you? Right? The ketchup may be in the same place it's been for 5 years, but when they want ketchup for their hot dog, they say, "Where'd the ketchup go?" Right? It's easier to come and ask you. And so when we set ourselves up as the founts of all knowledge for our children, right? They're going to think, "I don't need to learn because I can just go ask mom and she's going to teach it to me." So I think it's really okay if our kids see that we don't know everything, that there are things left for us to learn, and whether that's that we're going to learn it together with them, or maybe that we're going to send them off to go and learn it on their own. I think that that's a good thing. So I really want to encourage everybody that maybe is looking at some of this going, I've never heard of a secant before. Not that I can remember. Maybe I did, but it didn't stick, right? Or I don't know what factor by inspection means, right? Or unfactorable. I don't know. And that's okay. I really want us to be encouraged that that's okay. And I think it's probably better for our kids when we don't know everything. So let's take a minute because this is a common question that we get. And notice the top up here where it says order of operations, right? And we've given you two things. We've said we're going to simplify expressions, and we've given you this abbreviation, this acronym. And a lot of people go, well, why are we using this instead of, and I'm going to write it underneath, PEMDAS, because it feels like we're kicking Aunt Sally to the curb. And here's the long story. Lee said, I don't want people to just remember PEMDAS, right? I don't want to just teach PEMDAS. So I went and I spent a lot of time figuring out why, for myself, the order of operations was what it was, because I didn't know. I didn't know why we went in that order. I thought maybe we just all agreed, right? We're just going to agree to work in this order. And I discovered we didn't, that the order of operations is actually inherent to the nature of numbers. So to me, that's really kind of a big deal because it means that this is God's order of operations, not man's order of operations. So as I looked at that, and as I looked at how people around the world understood it, I realized that P is limiting. What does the P stand for in PEMDAS?
Parentheses.
Parentheses. Are parentheses the only thing that we can use to combine and show groups?
No, we can use brackets and braces and other things.
Yes, and
the notation.
They were before the
math map. They were before we were exposed to all these new symbols.
Right. So you guys, right. So there's some that are going, hey, I've been doing this for a while and I see a lot more, right? But there's all kinds of things that can express groups, right? When you think about a fraction bar or the division house with the vertical or the horizontal bar, or the horizontal bar that's part of the radicand, that's the vinculum, and that is a grouping symbol, right? Or we can look at our operations like sine that, and we usually do use parentheses, but it has an argument, and that whole thing, right, is a group. Its argument is a group. And so we decided to go with G to represent the fact that there's a lot more ways that we can group things than just with parentheses. So how about E? What did E stand for?
Exponents.
Exponents. So last week we learned that there were three operations that went together. What were the three operations that went together?
Exponents, roots, and logs.
Exponents, roots, and logs, right? And so if I just say exponents, I leave my logarithms and my roots sort of dangling out there, right? But notice if I use I for index, now I'm being inclusive and I'm saying all of these things that need to have an index, right, that have to do with my index. I'm going to take that and tackle that next. How about M and D?
Multiplication and division.
Now, how many of you have had your students or somebody else or one of those crazy like Facebook can you get the right answer types of things. And people think I have to do all my multiplication and then all of my division. Is that correct?
Yeah.
Well,
No.
from left to right.
I do go from left to right, but I do multiplication and division together,
Simultaneously.
right? Because they basically have the same weight, right? And we know that division, right,
It's the opposite of multiplication.
is like 1 over my multiplication, essentially. Right. And so, why we went with M was to really emphasize that multiplication and division have equal weight in our order of operations. We don't do one and then the other. And the same is true. How about our A and our S? What do they stand for?
Addition and
subtraction.
Addition and subtraction. And notice we just used addition for that same reason. So we took 6 letters, we've scrunched them into 4, but even in scrunching them into 4 letters, we've been more inclusive of all of the different things that we see mathematically. Now, I'm going to share a story with you that we had a family friend who had gone back to school as an adult to try and get his degree, and he was in a basic math class. And he came to me and he was trying to solve equations and he was really frustrated. And I said, well, he goes, I know PEMDAS, but it doesn't work here. And I said, well, yeah, but you can just go backwards. And he goes, and it was like, the heavens sort of parted. And he goes, why did nobody ever tell me that? Right? Why did nobody ever say it's this reverse process? So that's what we're trying to do here, right? We took this and we say, if I'm simplifying, I simplify my groups and I work my way out, right, to addition and subtraction. But when I'm solving, I'm working my way sort of in, right? I need to get into my group. So I'm trying to isolate my variable. So first I'm going to add or subtract. Then I'm going to multiply or divide. Then I'm going to clear any indices. And then I'm going to be left with whatever group I had. And then I might have to start the process over within that group. But that's why we really are stressing these two, because they are inverse processes, right? Solving is an undoing of a simplification in order to get that variable by itself. So I want to give you a minute to think about that. And then if you have any questions, please go ahead and ask them.
My question is, why hasn't anybody ever made it this simple before?
Because you had mathematicians teaching and they don't know English. That's the problem with modern specialists versus classical generalists. We all want to be brain surgeons, and we want brain surgeons to be specialists, but they're children first, and what a wasted opportunity education's been for the last 100 years.
Oh, so they subtract, so this.
I think
we also have teachers who aren't strong in math and don't have the confidence to look at things, so they are just doing what's been done every year, because why would we change something? It works, right? And so I would not have really thought about this. I'm going to be honest with you. I wouldn't have really thought about this if we hadn't said, I don't want to use PEMDAS. And so I went and worked and worked and worked and went, oh, wait, there's a better way.
The other reason I wanted her to change it was because all of these operations relate to the real number line. And what you're actually doing in every single problem is heading towards 0, the origin. And in real life, we're all headed towards our origin, Jesus Christ. And so there's so much philosophy behind solving problems too, that helps us to know God.
I think that's the big difference, is that the authors of the Math Map actually prayed and asked the Lord instead of just calling it Christian, as I've said before, by adding and subtracting and multiplying and dividing loaves, fishes, disciples, boats, commandment tablets. Like, that's not what makes it Christian. What makes it Christian is actually looking for God in the philosophy behind it.
I absolutely love that.
Well, you can
I
also
ha-
reason, with what we have, which is more general and, more internationally acceptable, and compare it to what PEMDAS and understand what PEMDAS is also.
Yes.
That way you can lead others to thrive that way also.
Yeah,
I
it's
had a
huge for
student, yes, oh, sorry.
No, go
I had
ahead.
a student yesterday. We were doing division and we were looking at the hops on the real number line. And I think one of them was the 12 equals 4 divided by 3. And he couldn't understand why the number line was going backwards. And it was, I think we were I think that's how it went. And I couldn't answer the question, but what I did say was, we're going back to our origin. And so, Lee, you just answered that. And so did you, Kirsty, in that we're all coming from nothing. So that is why we're going from the 12 and then looking at our units. Okay, how many hops did we take? And what is our number of units between on the number line in the in the exercise was it went from 0 to 4 to 8 to 12. And so I just said, how many do we have between 0 and 4, and then 4 and 8, and 8 and 12? And then how many hops are we taking? So I said, we're all coming from nothing. So I'm just reasoning backwards that's why we're going to the left. So our kids are even questioning this, at least mine were in the classroom. They just couldn't understand why we were going left.
Yeah, we glibly say things like, well, multiplication and division are inverse operations, but we don't really stop and think about what does that mean. And that's what we're trying to give our students the opportunity to think through. What does that really mean? And what does that look like on the number line, right? If multiplication always starts at 0, right? 3 times 4 is 0 plus 3 groups of 4. Well, division has to be getting back to where I started, right? But we don't often see that picture. So that's great that your kids are recognizing that. All right. Are there questions from last week, exponentiation, that you would like to revisit or that you maybe saw in the lessons?
I have a question. So since we have 3 functions for exponentiation, when we talk about having an inverse, I'm always confused. Do I have to list both of the other ones, or is there some connection between 2 of the 3 and then 2 of the other 3? Like, help me think about that.
Sure. So it really depends on what are the parts that I have. Right. So we know this is true. And that we can rewrite this this way. So it depends. I need to really have, I'm going to say this, 2 of my 3, right? To simplify, I have to have 2 of my 3 pieces of information. If I have 2 of my 3, then I can simplify that to find that 3rd piece. Now, when we get to functions, it's a little bit different because we're actually going to just know one thing, and we're going to then use variables for the other 2. But we're in 1D, and so we're just looking at one unknown. And so I need to know 2 of those. If I know the base and the index, I'm going to use exponentiation to solve for the power. If I knew my base, my power and my index, right, then am I undoing it to find my base? I am. So that's one way I could look at it as the inverse. But if I had known my base and my power, then my logarithm would be the undoing in order to find the index. So it really depends on what do I know and what is it that I'm looking for? What do I want to solve? Because it's a 3-part relationship, right? And a lot of times, right, we do that with the Trinity. We we might think, and a lot of denominations do this, they may focus on one or two persons. They go, oh yeah, there's a Trinity, but we really emphasize Jesus, or we really emphasize the Holy Spirit, or we really emphasize God the Father. But he is God in three persons, and you can't just take two, right? It's not a two-part relationship. So we can't take that three and make it just be two, because there's always three parts to the Trinity. There's always three parts to this relationship. And so when we talk about inverses, there's two, right? There's two inverses for each of these operations.
And so there's no weighting, there's not a weight that's higher on any of them. They're all equivalent to each other as far as how you would use them.
And I mean, for me personally, I think this was one of the most impactful moments where I had where math, right, and my faith came together. Because just like Lee just said, right, there's not a weight. One doesn't outweigh the other one. It depends on what I need. Well, there's days where maybe I need the comfort of the Holy Spirit, right? The comforter and the guide of the Holy Spirit. And so maybe that's the aspect of God that I'm really seeking out. Maybe other days, right, I'm standing on a mountaintop, or I'm watching a storm, and I'm just overwhelmed by Creator God, right? The God of the universe who created everything. And then maybe there's days, okay, so there are days, lots and lots of days, lots and lots of times every day, right, where I need the atonement of Christ, right? And I need him to advocate for me before the Father, because I need the blood of the Lamb to wash me clean, right? For forgiveness where I've messed up. And so, right, in any given day, right, I need all of the parts of the Trinity. In any given math problem, right, I might need all of the parts here. And the other two parts, notice, right, I don't just get Jesus, right? I might be like looking for Jesus to address the issue I have in the moment, but it's the Spirit and the Father who come alongside and enable, right? Or maybe when I need the comfort of the Holy Spirit, right? It's the Word of God that brings that comfort to mind, and time and nature, right? So like it all works together, even if I'm just looking for one.
Kirsty and I talk about this a lot, and I just want to keep including you guys. You know where we haven't, Kirsty, is with sine, cosine, and tangent. So between now and week 16, let's all think about that trinity of relationships.
All right. Any other questions?
Yes, Christy, I'm wondering, could you just repeat, last week we talked about when we see the number line increasing and then when we go backwards. Do you remember that? We talked about the circumstance when the number line looks like it's going up and then when it's going down.
Yes, I think I know what you mean.
I've been thinking about that all week and I haven't, so I'm just wondering if you repeat that.
If we are looking at, when we're looking at just the powers of numbers, right? So if I said to you, let's look at the powers of 10. Well, the 0th power of 10 is 1. The first power of 10 is 10. The second power of 10 is 100. The third power of 10, is 1000, and so on. And I would write them naturally from left to right, from smallest to greatest. When we're talking about place value, right, and I'm just going to draw a line to keep these two ideas separate. I have my radix point or my decimal point, and I go the opposite way. So I have my first power, my second power, my third power, and so on. And they get smaller on this side, and so on. And I made this comment maybe last week and even yesterday, I think, in talking to Lee, and I said, yeah, I don't really know why. And then it hit me, because if I took 1000 and I added 100 and I added 10 and I added 1, right? My thousands are bigger my 100, right? Just physically bigger. They have more places. And so it makes sense to do it that way, other than like somehow writing it out here, like my biggest to my smallest. So to me, it kind of makes sense. But that's what the difference is here, is that here I'm just listing these. This is just a sequence, right? From smallest to biggest of my powers of 10. When I'm dealing with place value, though, it goes backwards. So it's not really necessarily on a line. It's just that it's my place value. The order is different for place value than it is if I'm just listing those, right? If these were on, like, here we go. If I put these on a line, these I could definitely put on a line, right? And this would be a logarithmic scale because I'm putting the powers on and not the values. They're on a line now. And I could put those in order, whereas these are my place values. So they're telling me how much each of those spots are worth. Does that help?
Yes.
Okay.
So Jennifer, you or whoever said that, you said you were thinking about this week. Did you have any insights? Because I'm looking at what Kirsty just did and thinking, is there a reason they are opposite from each other? So now I have a whole new question to go to bed praying about. So did you figure it out?
No, I was just, and actually my husband was traveling, so I didn't get back to my notes like, for some reason, when she said this last week, it stuck out. And so all week I was like, in which circumstance were we seeing it increase, and in which circumstance were we seeing it decrease? And this is reminding me, yeah, in place value, and totally kids, like adults, we just take that for granted. Kids will point that out. So to sort of have an answer.
I do not have an answer, but I'm going to find one.
I'm kind of curious, does how in some cultures or some languages, they read left to right, some they read right to left, some they read from top to bottom. Does everybody do calculations like left to right? Do they write their numbers that way?
That's a really interesting, but here you go. We call these the Arabic or Hindu Arabic numerals, right? And Arabic, I think, is one of those less that does read
right to left.
Yes,
well,
right.
Well, Roman numerals do both, depending whether you mean
they're
subtract
mixed,
or add. They're mixed up. So that's,
right.
Because the position doesn't matter with Roman numerals. We don't care what the position is, right? Just like those Latin sentences, right? You can like throw your words in there and
right.
out. Our Roman numerals are a little bit the same, but when we're talking about place value, I wonder if it comes back from that idea of the Arabic, that Hindu Arabic influence on our numbers.
Well, it's further back than that, though, because of base 60 being the Old Testament's base rather than 10. So there's a lot of good questions there.
When we do division, we calculate from left to right.
Yep. All right, I'm going to go ahead and very quickly just take a look at some of the types of things you're going to see this week. So notice from the top of our page, we're looking at, again, functions. And so this is a way to help students see, right? I take my 3, I put it in here, and I get 3 squared plus 1, and that's 10, right? 3 cubed plus 1, that's 27 plus 1, and so on. So that's practicing that idea of a map from domain to range. At the bottom, we're looking at those inverse operations again. And I'm going to give you a little note here. This is going to end up in the errata. Right now, roots goes with powers, but we're going to put exponentiation here. Because, and here's a case where we're just picking 2, because usually the index is telling us how we move. It's not necessarily, right? It's part of that, right? I couldn't really do either of those without the index. But when I think of the movement on the number line, I'm usually thinking of roots or exponentiation. So, and then on the right-hand side, notice that we're looking at our intervals again. On this particular page, we're looking at unions of same order intervals. And so we're looking at where do they overlap and what does that look like when they do overlap. So when it's a union, we're saying it's this or this. Where is it true that either this or this is true? And no, it's going to be true for the whole thing. And so you're noticing in this case, we've got just different notations, all for the same solution. We just are looking at different notations. So we have we've got two that are going left, two that are going right, but again, we're looking at those notations there to compare our interval notation with our inequality notation. On page 2, we're doing the same thing, only now we're looking at some unions here of opposite order. So notice with these top 2 here, there's no overlap. So I just have to express that as a union, right? It's almost like having unlike terms, right? Where if I said 4x plus 4, it's just 4x plus 4. I can't simplify this any because they don't overlap. So I just have to talk about the 2 pieces. And below that, notice again, we're talking about unions where at least one is true. And so both of these end up giving me the entire real number line. On the right-hand side, I think these are some fun things that you could do with your students, because you could come up with making your own sets and ask them what are some things that belong in it, right? So for example, if X is a fruit and its skin is typically eaten, right? It'd be apple, pear, peach, and grape. So come up with some of your own set descriptions and have your students give you some ideas. And then down here, again, we're just starting to look at this idea that if the absolute value of B is 14, well, B could be 2 numbers, right? It could be 14, but it could also be negative 14. So here's an example where, going back to when we talked about equations and somebody said there's one answer, here's an equation that has 2, right? There's 2 answers. There's both the positive and the negative. I think in all of algebra that this is one of the more mentally challenging, like, to keep track of. Looking at algebraic absolute values is one of the more challenging things to keep track of, especially when we're looking at one variable. So we're going to be bringing our students along a little bit at a time, right, to help them make sense of this. So it's not something they necessarily have to understand all this year, but we're working towards helping them to understand something that I think traditionally requires a little bit of mental gymnastics to figure out.
Speaking of gymnastics, I'm waiting for one of you all to come up with a dance or movements or something for unions and intersections, because there's a pattern to the movement, but I don't have it memorized yet.
All right, so don't forget, we have lots of resources for our students, and we're going to practice that at the end of every class. And we have lots of resources for you. And so I've heard from some people lately that they're like, oh, I didn't know all of this content was in the companion. So I just wanted to take a minute. If you haven't been in the companion, this is the content that you're going to find. If you're a tutor, you're going to find a page that's just for you, and it has resources just for you as a tutor to be equipped and prepared for your community day each week. For parents, there is a little bit more information about the art, about the quotation of the person, and behind the quotation and the reflection. There is going to be more information on the I squared and the I cubed page. There is actually, if you click through on the math map, you can start to see where we're starting to put together where some of the lessons throughout the year review or preview one another to give you some of the ideas of where they intersect and overlap. There's going to be detailed content for the charts. So you can click on a different piece of the chart and get some detailed content. You can go to pages 1 through 4 and the tops. There's a walkthrough of the top problem on pages 1 through 4. Scattered around, there may be other content. So especially if we can frequently get the same question about a particular exercise, we may add some content in. So they're scattered around. I can't tell you exactly where they are because they're different every week. Because we are working with a mom out of Georgia, and we are adding slowly. We are adding chart references. So if you click on the bar on any particular page, you'll be able to click on that and see a list of the charts where you may want to go and get some reference. You can click again through those booklets, or from the main math map page, you can get to a glossary that has over 100 pages of words, along with detailed explanations, and along with images and symbols, including the instructional words we use and common symbols and notations in the math map. Back on that original page, there's like a who, what, when, where, why, and how of the math map. There's some, the original videos are available through the Math Map Book Club. Videos are available on that Math Map page. So there's a lot of content in there. If you have not gotten in there, I would encourage you to do so. We're constantly trying to make it better, constantly trying to update it and add content as we go. Our forums are getting ever busier. Babs and Shauna are doing a great job. If you have specific math questions, you can email us at themathmap@classicalconversations.com. You can also send us your typos and your errors. And then the beautiful thing is that we have community now over mathematics, and so you can work together there. So I just wanted to take a minute. If you hadn't explored those resources, I just want to make sure that you were aware of that. Next week, we are in 2D. I'm so excited. So much gets packed into our 1D lessons. And when we hit 2D, things become a little bit more cohesive in terms of like there's maybe not quite as much every week. And there's more of a pattern of restful weeks, and along with weeks that maybe push you a little bit harder. So if you've been like working really hard and you're like, I'm ready, you're going to breathe a sigh of relief. And I'm excited because Jill Philbrick, one of our other mentor tutors who's been piloting for years, is going to lead our discussion next week. So you're going to get another idea of what this would look like in community with somebody that right, because what I do is not what it looks like in community. We always want to be clear that, right, what I do is not that, because I cannot contain myself. But Jill is going to give you a better glimpse of what that would look like, and I know that you'll be blessed. All right, so I'm going to go ahead and if you have any last questions, we've hit our hour, but if you have some lingering questions that you just really would like the answers to before we finish, I am here.
Kirsty, can you write out the domain names so I can get a screen grab of it? Your handwriting of the domains.
Sure. So the math map domains or our numerical domains?
The math map domains.
Sure. So we have, and I'm going to, so we use, right, that's our symbol for naturals. And we use that with digits because the digits are a subset of the naturals. Then we have our naturals. We have our integers. Then we have several years where we are exploring rational numbers, because rational numbers are probably the ones that people are the most reluctant. I'm trying to think how I can say it, right? They're the most reluctant to calculate with. And we're going to change that, but we are going to look at them as decimals, and we're going to look at them as fractions. Then we're going to have another year where we're going to look at all of the rational expressions. And so that's going to include decimals, fractions, percents, and ratios. Then we have a year with the reals. And then we're going to talk about our complex, which is where we are now. Then we're going to use this symbol, and it's the symbol for algebraic numbers, because most of the work that we're going to do in algebra we're going to be working with equations that would have algebraic numbers as their solutions. So even though we may be looking at working with the algebra, the types of numbers that would be solutions would be algebraic. So that's why we're using that algebraic symbol. We're going to have monomials, binomials, polynomials. And you can notice here that monomials and binomials are subsets of polynomials. So there's things that are going to be true about all of those. And then we're going to look at expressions. And expressions are essentially going to be algebra where we can have a variable in the denominator or in our radicand. And then finally, we're going to have our transcendentals. And I'm not going to, they don't, dental, that's an L. There we go. Transcendent. No, it's just spelled wrong. Transcendentals. There we go. Transcendentals, because those are not algebraic numbers. And so we're not just using transcendentals though in that year to talk about the types of numbers that we're going to be looking at, but really emphasizing that, right, the long-term goal of the math map is, yes, we're going to learn math. Yes, we're going to learn how to calculate. Yes, we're going to learn how to simplify and solve all kinds of equations. But why? Why are we doing this? Because we want to discover God. We want to search for truth, beauty, and goodness. And those are the transcendentals, right, that we're trying to point to. So not just these numbers that are not algebraic, they don't necessarily feel familiar to us, but more than that, it's looking at math really holistically as a way to search for God and for truth, beauty, and goodness. And that's what that idea of transcendentals represents for our final year of the math map.
Mm-hmm. I love how you broke down the types of numbers that we're working in with the reals and the algebraic. That's a great picture. Great picture. Thank you.
Oh, you're welcome. Kelly, I see your hand up.
Yeah, so this is back from booklet. Well, I'm in booklet 3 here on page 1, but we saw it in booklet 2 as well. The bottom left corner, and I looked on the companion to see if there was any videos, but it was something my son asked me about, and we both kind of grappled with when we were doing math at home. And I know it says just to copy, so I guess at this point we're just becoming familiar. But I to the power of 2 equals I equals -1. Like how 2 numbers multiplied could be a negative was something that we were struggling with.
So that's the whole idea behind the imaginary numbers, right? Is that an imaginary number, right? That an imaginary number, let me just write this. If I square this, I get a negative. If it's a real number and I square it, I get a positive. Okay, and so that is the very heart of what we're looking at, is that, and I'm going to show you something that's really from lesson 27 because it's not one-dimensional, but it may help. So if I was to look at my complex plane, this is my real axis, this is my imaginary axis. If I was to look at 1 and I multiply 1 by 1, right, I essentially go 360 degrees and I end up back at 1, right? If I only went 180 degrees, right, I need something that if I multiply, right, times something and then times something again to get back to 1, well, that would be -1. Because if I go 180 degrees, right, times -1 is -1. If I go times -1, another 180 degrees, I get back to 1. Notice those are both real numbers. But now I say, okay, well, what if I only wanted to go halfway to -1? What if I only wanted to go 90 degrees? Right? So what is it? What can I multiply 1 by that when I multiply by it again, I get -1? Well, if I multiply it by the square root of -1, I get here to I. And then if I multiply it by the square root of -1 again, I end up at 1, right? And so that's my I squared is -1 because I multiplied by the square root of -1 2 times. Let's say I did it again. Now I have I cubed. Where do I end up? I end up at -I, right? Essentially I squared times I, -I. And if I went one more time, right? So times the square root of -1 again, where do I end up at? I end up at 1. So there's a geometric understanding of what we're looking at in this lesson, just arithmetically, right? That if I took the square root of -1 times the square root of -1, right? The square root of -1 squared is going to give me my -1.
That visual is super helpful. Thank you. I just
You're
screenshot.
welcome. All right. Leslie.
Okay, so I'm in the multiplication booklet 5. And I know this is not the first time that we see it, but in here, I'm like, okay, I've got to figure this out. So on page 1 on the bottom, that very bottom square on the left, and it says coefficient. So we're just underlining that term in our example. I'm struggling to understand coefficient, and I know I've used them before. I don't even remember how to understand them. I looked back at the definition in the glossary, and then I know we find coefficients when we do our imaginary number line, and I'm not grasping what I'm doing there either. Do you have any helps for that?
Sure. I'm going to just clear, I think I can do this. Let me clear this, and then we can. So I think, so, all right, if we think about coefficients, and I messed that up. Let me see if I can start this again.
Leslie, tell me also what page you're looking at. I want to make
So
sure.
it's page 1 of booklet 5.
Okay, that's what I thought. So
Bottom left corner.
You're looking at the 3 or 4 different words and trying to compare them.
Yeah.
By underlining them. Okay.
Yes.
So I think the easiest way to think about coefficients is that it's always about their position. Here we go, right? So if I'm thinking about coefficients, I'm thinking about where something is located, not necessarily the job that it's doing, right? So a coefficient, right? It's it goes with something. So almost always when I think of the coefficient, I'm going to think of it being a number that's with something else, or a literal that's with something else. Usually it's with a variable or with a unit. So if I say 4x or ax or 4 times 1 inch, right? In each of these, it's my number or my literal, because I can sometimes use that constant, right, as a coefficient. But I'm always looking at where is it located. It's not so much about the job that it's doing, but where it's located. And it's always going to be with something else. Now that's different to a scalar, because a scalar is about its job. Right. And so a scalar is something that is multiplying something else. Now I might say 4 is a scalar because what I'm saying is I don't care about its direction. It's just a number. But a lot of times we're going to see something like 4 with a vector, or 4 times x. Now here my 4 could be a coefficient, or it could be a scalar because it's doing the job of a scalar, but it's in the position of a coefficient, right? So these aren't necessarily, these words aren't necessarily mutually exclusive, right? One number
Okay.
could be doing more than one thing. Does that help any?
It does for there. So then on that same page, if we look up to that top box on the right-hand side where we're labeling the coefficients, so am I looking at the numbers next to the I?
Yes.
Oh, aha moment.
Yeah, sorry, I meant to put that under my example of coefficient and completely forgot. So
Okay. That's making a lot more sense. Thank you.
You're welcome. All right, Veronica.
Hi, thank you. My question's in book 6, the division book, and it's something that came up in the multiplication book, and I thought maybe I would get it by the next time I saw it, and I still don't. So it's on page 11 of the division book, booklet 6, and it's write the prime factors, that part I can do, circle the GCF, that part I can do, but then we get to underline and multiply the greatest unique power of each factor. And I do not understand that even a little bit. None of the factors look unique to me because they're repeated so much, and I have no idea how we get to the answer at the bottom of the page.
So one, let me let you know that we've wrestled with this because right, there's so often, because Lee will say to me, well, you know what you mean. And I don't, right? Because I've taken a big thought and I've condensed it down and I don't always communicate what I'm thinking. And then Lee and I will wrestle with things and she'll be like, okay, I think this is really clear. And then you guys read it and you're like, I have no idea what you mean. So I think that I just want to let you know that Lee has wrestled with these with me and herself, trying to come up with ways to really clarify this, that when we're talking about, so we're not saying the greatest is not an adverb that is modifying unique. We're saying if I had this list, I'm just going to like make up something. Right, if I had these two lists, I have no idea what numbers these are prime factorizations for, but these are prime factorizations for two different numbers. So I would say the unique factors I have are 3, 4, 5, and 6. And then I'm looking for my greatest power of each of those, right? So 3 cubed is my greatest power of 3. 4 squared is my greatest power of 5. 5 cubed is my greatest power of the 5s. And then 6, the 7th power of 6 is my greatest power there. And so that's what we mean. And so when we're talking about the greatest common factor and the least common multiple, my least common multiple has to have all of those prime factors, right? It has to have all of the 3s, all of the 4s, all the 5s, and all of the 7s, but I don't need right? So my least common multiple would be 3 cubed times 4 squared times 5 cubed times the 7th power of 6. My greatest common factor is going to be just the ones that I have in common, right? So in this case, it's really going to be almost the least. So my greatest common factor, I both have a 3 squared, both have a 4, both have a 5, but they don't both have any 6s. So my greatest common factor would be 3 squared times 4 times 5. And so that's what we're working towards on those that we're doing there. And the different ways we work through them in different exercises may demonstrate that differently, but that's the big picture that we're moving towards. Does that help?
I'm not sure.
So when we say the word unique, we mean we need unique numbers. So if there's a 3, 4, 5, and 6, you have to look at them all individually.
Okay.
But one problem may have a 3, like she showed you, may have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have to look at those uniquely and see what they do to affect the problem. That's all. We're just trying to, maybe there's ways, maybe say individual number. Here's the thing in trying to work it out. If you know your multiplication tables really well, all this is intuitive. but the language is hard. Kirsty showing you is probably the best way to learn this, is somebody showing you problems, which is the benefit of videos and book clubs. And why it's, we've read lots of math books. It's never expressed really clearly in language. So this was our attempt. So we will keep at it. If someone comes up with a better sentence, give it to me.
Okay, I guess as I'm looking at it, because in the book we've got to factor out 6, 16, and 24.
Yep.
And so I was looking at those, and maybe what you're saying is kind of, once I get each of those factors out, kind of comparing them for if their greatest common factor is 2, find the one that's got the most of that factor in it and use that and kind of go that way. Is that sort of in the...
That's what you're
All right.
doing.
So give me those three numbers again.
Yeah.
6, 16, and 24.
All right. Yeah, I do have my pen on. All right. 6, 16, and 24. So the first thing that you were doing was finding the prime factorization. So this was 2 times 3. This is 2 squared to the 4th power of 2.
Okay.
Right. And this would be the 3rd power, 2 cubed times 3.
Yep. Okay.
Okay. So
that part I get.
My greatest common factor, right? So I'm looking for what are the factors that we have in common. So my unique, maybe now that we're all well versed in what a base is, right? I could say, look at my unique bases instead of my unique numbers. Right. So now I'm not looking at the value. I'm just looking at the base. So I have, what base do I have in common here?
2.
2, right? I only have a 2. So what is the, right? I don't have 3, 4. I only have 1, right? That's in common to all of those. So my greatest common factor is just 2.
Okay.
Now, my least common multiple has to be a multiple of all of these. So that means it has to have a 2 and a 3. To be a multiple of 6, it has to have a 2 and a 3 in its prime factorization. To be a multiple of 16, it has to have 4 factors of 2. To be a multiple of 24, it has to have 3 factors of 2 and a factor of 3. So my unique bases would be 2 and 3. But I need to take my greatest power, my highest index or my greatest power of those. And so that would be my 4th power of 2 and my 3. And that's going to be my least common multiple.
Okay. That helped a lot. That makes more sense. So you're kind of doing that. You're looking at them and taking your greatest power of that greatest common factor and then your greatest power of whichever other factors and multiplying those to get your least common multiple.
Right.
Something that might help is this is where the frames, we had room for to explain it better to the adults than we do for the kids who are just practicing. So I would look at your frame and work through that problem really well. And then just Kirsty has a different problem in her chart that does it. So that gives you 2 more examples that are more at your level.
Okay. Don't overestimate my level, Lee. I'm right there with the kids.
well, me too. But you can follow it, I'm sure, because you followed this.
Okay, thank you. That example and seeing you walk through it like that, that helped. So thank you.
Yeah.
Oh, you're really welcome. All right. Any other last minute questions before we jump off? Well, thanks everybody for being here. And I look forward to seeing you next week. I know we're all going to be blessed by hearing Jill lead us through next week and get back to talk about more math. Have a great week, everybody.
Praise and thanks to both of you. I really appreciate it.
Yes, thank you so much.